This is a particularly timely moment to be talking about climate and energy. Let's see if the clicker is going to work. There we go. Because within the past 2 hours, the Department of Energy has published a report on climate science. It's now up on the website. I was one of 5 co-authors that responded to Chris Wright's request back in the middle of March to summarize the current state of climate science with a focus on how it relates to the United States. We wrote a report in about 6 weeks, focusing on topics that are treated by serious, established academic literature, that are relevant to our charge, that are downplayed in or absent from recent assessment reports, and that we had some competence in talking about. So this is the first time outside of the authors and some people in DOE that you'll be exposed to some of the points that we're trying to make. Well, the climate is changing. This is a perhaps familiar graph of the global temperature from 1850 up to the present, and the global temperature on average is going up. At the same time, carbon dioxide in the atmosphere is going up as well, and we know that that exerts a warming influence on the climate. But you can see it's not the only thing that's driving the climate, because in fact, the temperature went up for a while in the early 19th century. It then went down for a while, even though carbon dioxide was going up, and then it's been going up again more in the last 30 or so years. So that's a hint, as I'll try to emphasize, that the situation is not so simple that carbon dioxide from fossil fuel use is roasting the planet. When we think about what we might do about that circumstance, we have to strike a balance. On one side, there's climate science. What are the risks and benefits of a changing climate? On the other side, we've got the world's growing demand for reliable, affordable, and clean energy, and the technoeconomic realities that underpin that. We've already heard about the surging demand expected from data centers, but equally important, and maybe perhaps even more important, is the fact that there are 4 billion people on the planet who don't have enough energy, and as they develop, they will need more energy. And in striking that balance, it becomes then a moral, political question of values and priorities, tolerance for risk, equities across countries, across generations, and of course, the efficacy and the cost of anything that you might attempt to do to resolve the situation. Okay, let me start in a little bit on the science. And one important thing to understand is that human influences on the climate are a 1% effect. This graph from one of the recent UN reports shows the various influences, carbon dioxide up at the top, the largest, other greenhouse gases, methane, halogens, and so on. Some cooling influences, aerosols that we create exert a cooling influence, and the net. All of these are measured in the perhaps unfamiliar units of watts per square meter. To set a scale, you should know that the background power flow in the planet is 240 watts per square meter. And so in the total bar on the bottom, which is about 2.5, that's a 1% effect. That influence has been growing with time. This shows the various components of influence on the climate system. The purple graph up in the upper right is carbon dioxide going up and up. The black line is the total, and you can see it's going up and up as well. And so one point to take away is that if you see something happening before about 1930 or 1940, there were no human influences or none that were palpable at that time, and it's therefore a natural phenomenon as opposed to an anthropogenic one. The science that I want to focus on has been defined by a series of assessment reports. The UN the Intergovernmental Panel on Climate Change, puts out a report every 7 years or so. The most recent one, called AR6, the Sixth Assessment Report, came out in 21-22. The US government issues its own series of assessment reports called the National Climate Assessments, the most recent one, the fifth, in 2023. These reports, when you read them, they say important and sometimes surprising things. The problem is most people have not read the reports. The UN reports run to thousands of pages. I have read it, but I can tell you, you need to be a scientist to be able to understand it. Most people, at best, read the summaries for policymakers, and let me tell you that they are a pale, if sometimes misleading, reflection of what's actually in the reports. Let me start with a definition of climate. Fortunately, the Egyptians compiled for us an almost 1,000-year record of the height of the Nile River in Cairo. There's a structure there, the Nile odometer, which you can go see, that they use to measure the height of the Nile. And this graph is a graph of 900 and some odd years of the annual minimum height of the Nile. The Nile drains about 10% of Africa, about 1/3 of the continental US, so this is a pretty good measure of rainfall over a good fraction of Africa. And there are several things to take away from this graph. One is, year by year, it fluctuates a lot. Sometimes it's up at 5 meters, and then the next year or two, it's down at 2 meters. Right? Natural variability. Human influences were not present in the 15th century or before. The second to take away is that sometimes there are really high spikes, extreme events, or really low spikes, also extreme events, natural, entirely natural. The third is that if you average over 30 years, a running average, which is what climate is not what happens every day or every year. It's the long-term, multi-decadal, typically 30-year average. You get that red line. And even it changes a lot. And you can amuse yourself by imagining some medieval Egyptian climate panel screaming about new normal in the late 600s and 700s. And then if they just waited a while, it would have come back again. All right? So a little bit of humility as we think about the changing climate and what might be causing it. Here is a graph that surprises many people. It's right out of the UN report, buried in chapter 12, okay, all the way in the back. It shows about 30 different climate observables, temperature, heat waves, winds, rains, ice, and so on, and whether we have seen a trend that can be attributed to human influences in the past 100 years or so. And the surprising thing is most of the entries are white. We see no trend in hurricanes, in winds, in drought, in floods, and so on. Here's an example of some of that data. This is the graph of global hurricanes in the top left from 1980 until the present, so that's 45 years. And yes, it goes up and down a lot from year to year, but no long-term trend. The lower graph is a different measure of hurricane activity beyond account, and again, lots of ups and downs, but no long-term trend, and the reports say that. There is low confidence in most reported long-term trends in tropical cyclone frequency or intensity-based metrics. Tropical cyclones is the fancy scientific word for hurricanes or cyclones. Yes, we are seeing unusual heat over the last few years, and it is a mystery. Here is a graph of the global temperature as measured by satellites, month by month. The red line is the annual average, and this is since 1980 or 79, and you can see the recent years spike up. It's similar to other spikes we've seen in the past, but somewhat higher. The long-term trend may well be due in part to carbon dioxide, but the spike has been causing people a mystery, and the reason it's been a mystery is if you look at the reflectivity of the planet, how much sunlight gets reflected or how much gets absorbed, it's been going down for the last 20 years. Therefore, the planet is absorbing more sunlight, and therefore it's getting warmer. This is what's supposed to happen as greenhouse gases increase. The greenhouse gases affect the cooling power of the atmosphere, not the sunlight absorbed. So this is a big mystery at the moment, and perhaps a signal that we don't understand things as well as we think we do. Heat waves. This is EPA data, not from the present administration, but from the previous administration. It's up there on the EPA website. Heat waves. The current heat waves are no more common than they were back in the 1900s. And in fact, the greatest incidence of heat waves were in the 1930s, when human influences on the climate were less than a fifth of what they are today. Natural variability. All right, people dying from the heat. Well, maybe. But in fact, cold is much more deadly than heat. This is some data about fatalities due to cold, both extreme and moderate, the blue bars, and heat, both red and orange. And in fact, cold-related fatalities are 9 times more common than heat-related fatalities around the world. So as the planet warms, the death rate from extreme temperatures is actually going down rather than up. A word about fires, much in the news. From the US government assessment report a few years ago, state-level fire data over the 20th century indicated that the area burned in the western US decreased from 1916 to about 1940, was at low levels till the 70s, and then increased again. There's the graph. Fires were much more common in the early part of the 20th century than they were in the latter part, and the reason for that is Smokey the Bear, right? The Forest Service started a deliberate policy of suppressing forest fires before they could grow. The fires are, of course, a natural part of the forest ecosystem, and so when you suppress them, you get that. Montana in 1900 compared to Montana in 1981, a lot more wood to burn. And so it's not surprising that when it does burn, it's going to make a lot of trouble. So the recent fires, I think everybody agrees, are some combination of forest management practices, development, putting towns in the middle of the forest where they probably shouldn't be, and then drought conditions, whether that's natural or anthropogenic. One can have a discussion. I've got to say a word about the Texas floods, because we only uncovered this in the last few days. What I show you here is the Weather Observer's report from July of 1900 for Kernville, Texas. Right? You remember Kernville, where all the floods happened, right? And if you look, I don't know if it's legible, but if you look at around the 15th of the month, there are 2 days where there were 11-point-something inches of rain fell and 3-point-something, so a total of 13 inches of rain in those 2 days. And you can see the observer's notes in script on the right part of the report saying that the river, the Guadalupe River, went up by 33 feet at that time. 1900, right? Okay. Here, in fact, are the 22 heaviest 2-day rainfalls in Kerrville from 1893 up until today. And you can see that the 2025 event doesn't even rank. So it's happened before, and it was, I think, irresponsible to have the kind of development that happened on the river, which really caused the catastrophe. So people don't even prepare for the past, all right? So again, attributing this to carbon dioxide doesn't fly logically because, in fact, it happened when carbon dioxide was not a factor at all. All right, let me talk about projections to future climates. They are, by acknowledgement of the experts, not fit for purpose. Remind you that it's a 1% effect, human influences, on a chaotic system where we have poor data. The oceans are really important for climate, and we don't know very much about what happens in the oceans. It is a grand computational challenge to try to project the climate over the next century, let's say. What's done is to cover the Earth with squares of about 100 kilometers on a side, build 30 voxels up into the atmosphere, 20 voxels down into the ocean, and then use the basic laws of physics, conserving mass, energy, momentum, radiation, flowing through those boxes, time-stepping it 10 minutes at a time. Do that for a couple centuries, and you do it without carbon dioxide, and then put the human-caused carbon dioxide in and see how things change. The world has about 40 different models that disagree with each other and largely disagree with the observations as well. There are problems. There's what's called subgrid parameterizations. The boxes are not fine enough to resolve all the details. A box 100 kilometers wide can't resolve a thunderhead, which might be 5 kilometers wide. And so you have to make assumptions. Different people make different assumptions, and so you get different answers. Most vexing are feedbacks, clouds. When the globe gets warmer, there'll be more water vapor in the atmosphere. You might expect that there were more clouds. Where are the clouds? Low-lying clouds cool the planet. High clouds warm the planet. And so you have to decide. You have to try to do that on the basis of physics and observations. Again, people make different assumptions and get different answers. And then the climate system has its own internal changes that happen. Here I show you a graph of some changes in the Atlantic called the Atlantic multi-decadal oscillation. It takes 60 years to play out. The models barely show these, and when they do, they're not of the right timing and the right magnitude. And in fact, as people have built more and more sophisticated models, they haven't converged much over the last 15 years. Let me show you some examples. This is a graph of about 40 different models, and what's graphed for each model is how sensitive it is to carbon dioxide. The yellow bars have been deemed by the UN to be too sensitive and thrown out. It's kind of disheartening that the world's best modelers can't get it right 40% of the time. For amusement, by the way, the least sensitive model is the Russian model down in the far right there. Canadian model is awfully sensitive, actually. This is how bad the models do when you ask them to reproduce the temperature over the last century or more, 140 years. The black line in each of these graphs is the observations, and the different traces are the different models. And the models get it wrong by more than the amount we're trying to describe. So this is not very good. Here's more. This is many different models trying to reproduce the difference in reflectivity between the northern hemisphere and the southern hemisphere. Observationally, it's the black line. Namely, there's no difference between the northern and southern hemisphere. Some of the models get it wrong by several watts per square meter, again, as much as you're trying to describe for carbon dioxide. You might say, what about regional predictions? This is the warming trend in the US Corn Belt, 11 states, Iowa, Nebraska, et cetera, for the years 1973 to 2022. The red bars are the models. The blue is the observations. The models in general are just much too warm. To say what the climate's going to be 50 years from now, you got to say, what are emissions going to be? And consistently, projections of emissions have been too high. This shows a set of projections of emissions made at various times. The black line is what actually happened, and you can see that, in fact, we have been overly pessimistic about emissions. I'm not going to go through this one. It's a little bit too complicated. All right. Predictions, sea level rise, are remarkable. I lived part of the time in the New York City area. There has been a tide gauge at the Battery, the southern tip of Manhattan, since 1850, roughly. This is the sea level as measured by that tide gauge. When you ask how fast is it rising, the black curve shows the historical data taken from that blue graph, and the NOAA projection issued in 2022 says that rise indicated by the red star is locked in. It will happen no matter what. Well, who am I to challenge NOAA? Okay, we shall see. Okay, we shall see. Is warming bad? Well, it's interesting to take an historical perspective. Since 1900, we've seen about 1.3 degrees Celsius rise in the global temperature. What's happened since 1900? Well, population has gone up by a factor of 5 globally. Life expectancy has gone from 32 years to 72.5 years. The literacy fraction has gone from 20 to 86%. The GDP per capita has gone up by a factor of 7. Extreme poverty has fallen by a factor of 7. And the death rate from extreme weather events has gone down by 50 times. If you believe that the globe is going to warm by another 1.3 degrees, which is about what the IPCC says, the UN panel, it's hard to believe that this is going to get derailed. Agriculture has benefited enormously from increased carbon dioxide. Remember that we pump CO2 into greenhouses in order to get the plants to grow better. And in fact, rising CO2 levels globally have palpably greened the planet. Weather disasters, as a fraction of GDP, have actually gone down over the last 30 years, and they hover at about 0.2%, so not very much. Most people recognize this. Even the Biden administration recognized this. This is a graph of the projected impact on the US GDP in percent, plotted as a function of the temperature rise globally. This was put out in a report by OMB and CEA, the Council of Economic Advisors, in 2023. You can still find it on the web. And what it shows is 12 different predictions from the peer-reviewed literature. The black line is the average of all of them. And it can be summarized as a few percent for a few degrees. Namely, if the global temperature goes up by a few degrees, the GDP will be a few percent smaller than it would be otherwise. And what that means is if the GDP were growing at, let's say, 2% a year for 70 years, instead of being 4 times bigger at the end of 70 years, it would be 3.86 times bigger at the end of 70 years. Too small to really resolve or to predict. Right? So even the Biden administration said this quietly, even as the president was talking about an existential climate threat. All right, so what are we going to do about this? Greenhouse gas emissions have been going up. They're at record highs at the moment. Some fraction of the world's diplomats are trying to get to net zero by 2050 to avoid the worst effects of climate change. And the trajectories shown for emissions out to 2050 are there. Needless to say, the world is currently at the top, and prospects for getting down are pretty dim. The world is trying to make, or has tried to make, an energy transition to reduce emissions. I like to use the following picture to describe the energy transition today. The world charged off saying we're going to reduce emissions, and it suddenly realized that there are some fundamentals that spell a very bad outcome for that effort, just like Wile E. Coyote. What are they? Fossil fuel use and greenhouse gas emissions are at or near record highs globally, despite 10 years of trying. Energy security has displaced emissions as concerns in Europe and Japan. The annual meeting of 200 some odd countries, which happened last year in Baku and in December happens somewhere else, I've forgotten where, has turned into basically an extortion fest for the poor countries from the rich countries. We see the ambitious goals that were set for reducing emissions backing off in the US and the EU. There's popular and political pushback for green transitions, and climate finance has crashed. Western automakers are retreating from electric vehicles. The root causes are growing demand. The world needs more energy. That is the primary concern. Fossil fuels right now are the most reliable and convenient way for them to get that. Geopolitical instability threatening energy security. Energy systems take a long time to change. It's taken 100 years to build the US energy system. It's going to take another 100 years to change it. The energy transition is expensive. It's disruptive. We've seen indications of that already. In the US and Europe, we should have adopted the attitude that President Xi has articulated for China. We're not going to change our energy system until we've got something better. And we do not have that at the moment. And there's a fading perception of the magnitude and urgency of climate risk, as I've tried to show you the data actually say. The words catastrophe, crisis, existential have no place in describing the climate situation. So I would summarize in saying climate ain't nothing, but it ain't everything. What would I do if I were in charge? Cancel the climate crisis, but acknowledge the task and challenge of reducing human influences. We need better representations of the science and the technologies to non-experts, and the report I described for you is one attempt to do that. We also need energy and climate literacy for the public and the decision makers. We need to keep observing the climate. One of the things that disturbs me about the current administration's push is to cut back on climate observations. The effects are small, they play out over a long time, and unless we're watching continuously with high precision, it's not going to go well. We must not constrain the developing world's energy supplies. It is immoral for the developed world to tell people in Vietnam, you can't build a coal plant. They need that energy. We need a much greater focus on adaptation and resilience. We don't really have a good framework or good sense of the costs. And we need to promote development and resilience in the developing countries. And then finally, R&D, develop and demonstrate emission-light technologies. Fission is high on my list, nuclear power. I'm a nuclear physicist by training, so the atom is my friend. And when I was in the Department of Energy, we hoped to get the small modular reactor program underway. Fusion is down there. I can say some words about that in the Q&A if people are interested. And then we need to understand how to do this gracefully, respecting the technology development, the economics, behavior, and then move slowly to reduce emissions. It's not a crisis. And steps that we might take thinking it's a crisis will be more damaging than the change in climate itself. Thanks for your attention.